Thank you very much to the organizers for the opportunity to speak here. It's really, I was just telling them before we started, it's um, uh, amazing that they keep this going, and it's such a great service to the community. So I'm really grateful to them for yet another opportunity to speak to you. So this is a number theory seminar, so let me go really, really slow and start at the very beginning. So when we were talking about spanning trees of graphs, so G will be a finite graph, and tau of G is the number of spanning trees, So maybe we want, since we want there to be some spanning trees, we'll make these graphs connected. And let's make them simple, so there are no loops, no self loops, no connections from a vertex to itself, and no multiple edges from two vertices. So these are both out. And so the number of spanning trees is something that's been studied for a really long time. I think 1847 is when Kirchhoff proved the matrix tree theorem. So he was studying resistance in electrical circuits and needed to know what all the different ways, if you have some complicated electrical circuit, what are all the different paths that electricity could take, and realized that, well, that's the number of spanning trees. And he realized that there was a Laplacian, there was a spectral mechanism by which you could calculate this. So this is the matrix tree theorem, which is that this tau of G, how do you compute? I give you some complicated graph. How are you supposed to get your hands on the number of spanning trees? It's actually pretty easy to compute. It's just the determinant of a minor of the graph Laplacian. And I even wrote this down the other day, 1889, Cayley was looking at this. And so there's something called Cayley's formula, which is that if you have a complete graph, so if I have a complete graph on n vertices, then we know exactly what the total number of spanning trees is. It's n to the n minus 2. So it grows, potentially super exponentially. Now, curiously, Cayley's formula is an easy consequence of Kirchhoff's theorems. I don't know why it has a special name, and it was also known in 1860 to Burchard. So this formula was proved independently by Burchard in 1860. Anyway, this quantity. I just want to impress upon you that this quantity is sort of very old and very natural from lots of different viewpoints. This even arises in evolutionary biology, apparently. If you look at phylogenetic paths, that if there's some let me not diverge too much from what I want to say, but you can imagine if there's some mutations that you want to track, well, what are all the different possible ways that mutation could be tracked? That's the number of spanning trees. It arises also in Lubotsky-Phillips-Sarnak, so for Ramanujan graphs, so this is Lubotsky-Phillips-Sarnak. Phillips-Sarnak, 1987 or so. So it turns out that tau, the number of spanning trees of these graphs, is actually measuring the class number of a certain function field. So there's all kinds of fascinating connections between these. Now, in the 1960s, a guy named Sedlacek, Czech mathematician, started to study, initiated a study of tau in families. I mean, I guess you could say Cayley was studying tau in the family, but the family is all complete graphs, which is a pretty thin family. But we can look at larger families. So the families that he isolated, so we'll say F is a family of graphs, and let's grade the family by the number of vertices. So this is things with n vertices, the graphs with n vertices. And some families that Sedlacek studied is, well, the family of all simple connected graphs. He looked at k-regular graphs. So k-regular graphs on n vertices and what happens to the numbers of spanning trees. So by the way, these are all, the Ramanujan graphs are all k-regular, 3 regular in the original construction. And he also asked about planar graphs. And so, well, let's just get started and see what this looks like in families. So let's do an example. Let's look at F4 for all graphs on 4 vertices are anyway planar. So we may as well.
I'm sorry? Yeah. Can you hear me?
Yes, we hear you.
Thank you. Yes, I'm just curious about you said in the Swee Phillips rank, they identified tau of G to be the classical function field. I was wondering which function field.
I'm sorry.
We cannot hear you well, so
yes.
can you please fix your...
Oh, which function? I see it's in the chat.
Yes.
Yeah, there's an explicit description. Yeah, it's in their paper. It's a very simple observation. So in terms of F4, let's just write down what all the different graphs are on 4 vertices. This is, I think this will put us in the right mindset. So let's start maybe with, we could either start with the smallest or the largest. Let's start with the largest. Let's start with the complete graph. So here's the complete graph, A4. We can take one edge away, and now we have, I don't know what to call this, K4 prime or something, K4 minus an edge. We could take the middle edge away, and that will give us the cycle, the 4 cycle. We could also have taken away one of the other edges. So that would leave us with a triangle and an edge. I don't know what to call this, triangle and tail. We don't need to name them. And that's basically the only ways that we can remove one edge from these graphs. Now from each of these, let's see, from C4 I can drop one edge and just get a path. So this is P4. From here I can't drop that edge because it won't be connected, but I can drop that edge and get P4 again, or I can drop that edge and I'll get the star. So what does that look like? I guess the star graph looks something like this. So this is S4, the star graph. Okay, does that make sense? So these are, I think, 1, 2, 3, 4, 5, 6. I think that's the 6 graphs on 4 vertices. And so let's look at their number of spanning trees. So tau, we just said we have Cayley's formula. So tau of the complete graph on 4 vertices is 4 to the 4 minus 2, if you remember the formula right there. Because this is when n is equal to 4. 4 squared is 16. So this is 16. For this graph, it turns out one easy thing you can do is just notice that half of the spanning trees will use this edge and the other half won't. And so this, the total number of spanning trees here drops by a factor of 2. Let me go over here. P4, the path on 4 vertices, is already itself a tree. So there's only one spanning tree. There's no other edges you can take off and still have it span. Same with S4. What about this guy? Actually, you can't drop this edge to make a tree, but you can drop any of these 3 edges and that'll get you a tree. So you can drop 3 edges, which means there are 3 distinct spanning trees. And for C4, you can drop any one of these 4 edges and get a tree, a spanning tree. So there are 4 possibilities. Does that make sense? So if we let T, and the family is implicit, T of n is just the image of tau on Fn. Then T of what we just computed is T of 4 for either all or planar is which numbers occur. 1 occurs, we don't care about what multiplicity they occur with. So 1, 3, 4, 8, and 16 are the numbers of spanning trees.
Sorry, Alex, there is a question, yes.
Yeah, so this could either be all or planar because all graphs on 4 vertices are planar anyway. Only when you get to graphs on 5 vertices do you now have, the complete graph on 5 vertices is not planar. So that's where these two would be different. These are not K-regular, so it's a different family. Just to for planar, so tau planar of 5, just to put it up there. I wrote this out. I worked this out for myself. If you get bored with what I'm saying, you're welcome to do this exercise. But you get 1, 3, 4, 5, 8, 9, 11, 12, 16, 20, 21, 24, 40, 45, and 75. Okay. Notice that you do not get 5 cubed. 5 cubed is Cayley's number, 125, and this is not in the set of, the connected graph, the complete graph on 5 vertices is not planar. Okay, does that kind of clarify things? In just a minute, I'm going to restrict our attention exclusively to planar graphs, but I want to kind of give you the big picture before we do that. So far, so good. Any questions? We haven't done anything really. Okay, so what Sedlacek started to study is the growth. So Sedlacek, what is the growth rate of T of n in various families? So let me specialize, since we're getting a little confused about different families. Let's restrict our discussion. Maybe at the end I'll come back to other families, but let's stick to planar graphs for a second. So here's an easy some observations, easy observations. First of all, 1 is always in Tn because you have trees. A tree, if you're already a tree, as we saw here, there's lots of different trees, and they all have one spanning tree. So 1 is always there. By the way, 2 is never a spanning tree number, because if you have 2 spanning trees, there's always a third somewhere. We can observe that n is always in T of n. So that's because you always have the cycle. The n cycle will have exactly n spanning trees. Another thing you can observe is that these spanning tree numbers are nested. So 1, 3, 4, 8, and 16 all appear again here, and that's for the very simple reason. So let me write the nesting. Tau of n is always contained in tau of n plus 1. You can take any graph and just add some random tail to it, and that won't change the number of spanning trees. Okay, so you can keep the number of spanning trees. Whatever numbers of spanning trees you already had, you can keep. All right. So what can one prove? So these are some easy things. Another easy thing is that if G is planar, so if it's in the family of planar graphs, and the number of vertices of G is n, then G is at most, let me be crude and say something like 8 to the n. Doesn't matter. This is some constant. Maybe I should just make it a constant. Then, so there exists a constant, so that if G is planar, then it grows. So these graphs grow at worst planar. There's a question. Indeed, you can.
No, it's
sorry,
an answer to the previous question.
Yeah, can we say that Fn is the set of all connected spanning graphs on n vertices, depending on which family? Yeah, depending on the family that we're looking at. Now we're looking at planar graphs. So Fn, in this context, Fn is connected spanning graphs? No, just connected. So connected means that it has some spanning trees. And now we're restricting to simple and plain. Okay, so what this means is that, of course, so this has the obvious corollary that the number of spanning trees, if these numbers are bounded at most exponentially, then this also there's at most exponentially many values, distinct values of numbers of spanning trees. In the opposite direction, so Sedlacek already himself proved, this is in 69, proved that the number grows at least quadratically. And there was more recent work on this, so Azaria, I'm skipping quite a bit of work, but more recently, Azaria showed that this is at least e to the root n. I'm ignoring some log factors. And then Stong showed in 22 that you can get a little bit better and get up to n to the 2/3. Now, one of the difficulties, this really 2/3, there we go. One of the difficulties is the number, so let me throw here a little, another remark. The size of the family, the number of the number of non-isomorphic planar graphs on n vertices itself grows exponentially, is e to the omega n. So you might say, well, you have lots and lots of graphs. Why can't you make lots and lots of distinct values of spanning trees? But the number of trees on n vertices is also exponential. And so if you think of Fn as this big blob with exponentially many things, and tau is some function that drops you onto, some range from 1 to c to the n, well, the preimage of 1 is already exponentially large. And you're trying to see how many distinct possible values you could get here. Okay, so it's very hard to produce lots of distinct values of spanning tree. Does that make sense? Nevertheless, so we now have a complete understanding of this. Well, we at least qualitatively, without specifying what the constant is. So this is a theorem. This is joint work with Swee Chang and Igor Pak, and this is on arXiv already. The theorem is that indeed tau of n grows exponentially. So there exists a constant bigger than 1, so that we do have at least exponential growth and at most exponential growth, so we kind of know everything qualitatively about this growth rate. By the way, this is new even for the family of all graphs. It was not known prior to our work that there are exponentially many distinct values of spanning trees on n vertices without the restriction to planarity. Of course, for all graphs, it's not the end of the story, because the upper bound isn't exponential, it's super exponential. It's n to the n for a connected graph. So there's a lot more room for all graphs. I'll come back to that later. Okay, is the statement of the theorem clear? Any questions?
There is one question from Christoph Lloyd.
To be sure, you want to count the number of different values that the matrix minor determinant can take in the family. Yes. Why is this number interesting? Well, I tried to illustrate the various ways that it arises in lots of contexts. But indeed, I think there wasn't. I think I talked to Noga Alon recently about this work, and he had referenced it previously, but I don't think he looked at it seriously. I don't know how much interest this problem had in the graph theory community, which, of course, I'm an outsider, so this is all news to me. Anyway, so this is the problem. We want to understand what happens to these numbers, and in fact, we show much more. So, in fact, this constant, if you look at how many distinct values there are of Tn among the first exponentially many, this is a positive proportion. So there exists a constant greater than 1. I mean, it's a restatement of the same thing, but this has a positive lim-inf. So divided by the number of elements in this range, this limit is positive. And in fact, you could do even more. One could prove, moreover, that that there's a range for which this limit actually is 1. So in other words, 100% of numbers, you start to see this a little bit here. So the tail gets sparse, but at the beginning, the farther and farther out you go, there's an exponentially large range where it seems like almost every number is occurring. Of course, it can't be every number because 2 will always be missing, and but every number other than 2 will eventually arise. That's because of that's because of this observation. So every number does eventually arise. Of course, this is for n greater than 2. So every number eventually arises, and in fact, what we conjecture happens is that every single number will occur, and I'll explain why that's a conjecture. Okay, so the proof of this theorem has sort of 3 steps. So three steps. I'll try to illustrate it like this. So step 1 is to dualize. Explain what I mean by that. Step 2 is to reduce, well, maybe there's 4 steps. I don't know, some number of steps. We'll find out how many steps. Step 1 is to dualize. Step 2 is to reduce the graph theoretic problem to a dynamical problem. Let's call it Diophantine approximation, to a problem in Diophantine analysis. Step 3 is to reduce Diophantine analysis to a problem in dynamics, I guess one could say. And then eventually just do the dynamics. Okay, so that's the rough outline. Yes, Jordan, these numbers look fairly composite. And it sounds like you believe infinitely many primes occur as tau of a graph, but is this provable? Yes, in fact, the rate, not only do we know, so one can prove that this number is 1 with a rate, even with a power savings. So a power of this savings. So this is c to the n 1 minus epsilon, or some smaller c to the epsilon. And so as a result, you'll get, almost every prime will occur as a number of spanning trees in some graph. Yeah, okay, well, CP, right, CP has exactly P, has exactly P spanning trees, but you'll see in a second, we want the relationship between the number of spanning trees and the number of vertices should be exponentially large. You'll see. Okay, so let me get to that exactly right now. So let's do step 1. So what do I mean by dualize? So it's almost like taking a transpose. If we think of n, let's say n going this way, so n is 3, 4, 5, 6, and so on. This is the number of vertices going this way. And we think of the numbers and t of n going this way. So there's 1, 2 will never occur, 3, 4, 5, 6, and so on. So I'll put, so in the case of, what was t of 4? Let me put t of 4 here. It was 1, 3, 4, 8, and 16. So what I have in mind is say, yes, 1 occurs, 3 occurs, 4 occurs, not 5, not 6, 7, 8, yes to 8, and yes to 16. So that's what happens for 4. And then for 5, some more things happen. in addition to the ones that were here, maybe 9 occurs or 11, some more numbers like this, and then there's a bunch of x's. Okay, so I want to just dualize this and let tau hat of t. So if t is the value of tau, this is the set of n, the set of numbers of vertices, so that there exists a graph in your family on n vertices having tau exactly equal to t. Okay, so if we look at tau hat, well, of 1, we just get every value occurs because 1 is always there. So tau hat of 1 is, I'm only taking at least 3 vertices in the graph. So 3, 4, 5. So we get everybody. In fact, whereas tau hat of 5, yeah, so 5 will occur in 5. So tau hat of 5 is everybody from 5 and then on. 5, 6, 7, and so on. So what I hope is clear, so the observation is that tau hat has some minimal value. Let's call that minimum value alpha of n. And then is every number thereafter. Alpha of n plus 1 and so on forever. So where alpha of n is, of course, the minimal number of vertices of a graph, the minimal n for which there exists a graph on n vertices having tau of g equal to, sorry, this is supposed to be a t. So it's the least n for which there is a graph on t vertices. Okay. So what we know is that,
I'm sorry?
yes.
This property of stabilization, this is only true because you're considering a family which remains in the family at the next step by adding one edge, right?
This is true in the families of all graphs or the family of planar graphs.
Planar graphs, okay. But if you fix to K regular or some classes...
It would not be necessarily true for K regular.
Okay.
That's right. So I'm sticking to planar for probably the rest of the talk. We'll see how far I get. Is it possible to find the supremum of tau? In the case of planar graphs, we know that planar graphs grow at worst exponentially. This is what I was saying here. If the graph is planar on n vertices, then the graph grows at worst exponentially. So the supremum, what you can do is take, are you asking for the value of this constant, maybe? So the value of this constant, people have worked on the value of this constant, and I don't remember what the world record is. But I'm not worried. I'm not looking right now for quantitative growth rates, just qualitative, exponential. Okay, so because of this nesting property, once you have the value once, then it continues forever. So this is what I wanted to say about CP, is that yes, you do have exactly P spanning trees on CP, but actually the value P will occur much earlier, is what we claim, will occur much earlier in the sequence. So the fact that graphs, so tau of G is at most exponential means that there's this exponential barrier. So here's the graph of this exponential function. There's an exponential barrier after which everything must be x'd out. Okay, so conversely, so what that means about alpha t is the least. So if you have some value of t and you want to know what's the first place where you get a check mark, and after that you always get check marks. So this lemma, this comment has a lemma. The lemma is that alpha of t is at least grows like log t. Okay, so when you're using CP to find the prime p, that's overkill. You should use something of size log p to find that prime. Does that make sense? And so the question is this bound really best possible? And so this is where Stong's theorem, again from 22, is that there exists. So what you have to do to prove this theorem is construct some graph on n vertices with exactly t as the number of spanning trees. And Stong did this with, so this is big O of log to the 2/3. There's log factors that I'm suppressing, maybe over log t, something like that. Okay, and so it's this that corresponds when you dualize to the theorem I claimed here for Stone. This is the n to the 2/3 exponential growth rate. Okay, and so so here's the main lemma. Maybe I'll call this, yeah, we can call it a theorem. So the main theorem is the following. Suppose that you have a fraction, p over q, which can be written as a continued fraction expansion in the following way. So I'll write it as, let's say it's in the unit interval. So the first partial fraction is 0, then a1, a2, up to a, we'll want it to be even, I'll say 2k. Suppose that p over q has an expansion like this, where a2 and a4 and all of the even values are equal to 1. So in other words, it's something, then the next partial quotient is 1, then something, next partial quotient is 1, and the last partial quotient finally is 1. Then there exists a graph with tau of the graph being exactly q, this denominator, such that the number of vertices of the graph is less than log q.
Sorry, Alex, the lemma and Stong, is there a log missing in Stong's result, or it looks like they contradict one another? Lower t and upper bound log t.
Sorry. What this is saying is, yeah. What am I trying to say? I'm trying to say that this says that. So we have this upper bound. What I want to say is that alpha of t, yeah, what I mean to say is big omega. So it can be as large as log t, and the question is it as large as log t? Is it big O of log t? Okay. So what we want to show is that if you go to some value of t, so what we want to show is that for 100% of the values of t, when you look down, you do see check marks as small as log t. Okay. Thanks for that question. So what this says is if you have, so why does this main theorem imply our other theorem? Well, hopefully it's clear that we can construct graphs with log q vertices having, where we have exact control on the number of spanning trees. And that will imply that as long as we can find these fractions, these p over q's, so yeah, let me write something down. So if, well, let's make it a little theorem. Let me make a conjecture. Here's a conjecture. Here's a kind of a bold conjecture. Why should this be true? Yeah, I'm missing one little thing here. So let me make this more precise. Let me make this more precise. This is bounded by, let's call this A1 plus A3 plus A, well, 2k minus 1. Okay, roughly. So here's the conjecture. The conjecture is that there exists some absolute bound so that for all q may be sufficiently large, there exists p co-prime to q so that the continued fraction expansion of P over Q, again, it's some A1, A2, and so on, A2K, has the even values are all equal to 1, and the odd values, which in particular means all values, are bounded by A. Suppose that this exists. So again, suppose that there's some absolute bound, like 1,000 or something. There's some value of A, so that every denominator arises in a fraction where the partial quotients are all bounded by 1,000, and every other partial quotient is equal to 1. What does that mean? So this conjecture, so here's a little, I don't know, corollary. The corollary is that this conjecture implies that alpha of t indeed is bounded by log t. Okay, and why? So this is hopefully clear from the main theorem. Maybe this is the main graph theorem. This is the main graph theorem. So the proof is very simple. So if this holds, if conjecture holds, then you pick your t, set t equal to q, find a p with this property, with Diophantine property. And now use the main graph theorem, and then use graph theorem to make a graph where the number of vertices, it's this sum, but this sum is, it's easy to see that if the partial quotients are all bounded by A, then this denominator is also, then this sum is bounded by log of the denominator. Okay, in which case alpha of t is always at most log t. So that reduces. So this was step 2, I guess. We reduced, we dualized, and then this is step 2. Step 2 is this main graph theorem that reduces. We've dualized, and then we've reduced graph theory to a question in Diophantine analysis. Now, it's enough you don't need the full strength of this conjecture. You don't need that every Q occurs this way. You could have 100% of Qs. You could even have a positive proportion of Qs occurring this way. So enough to have, for the exponential growth, for the main theorem, this exponential growth here, for this main theorem, in fact, it's even enough to have just some power of Q arising. Enough to have the number of Q up to X, for which there exists a P satisfying the Diophantine property with Diophantine property. Is at least some power of X. Because then you'll get exponential growth. But if you want to say even more, in fact, we prove that this number is at least X. And again, one can prove, with more work, one can prove that it's actually asymptotic to X. Okay. So let's talk about this Diophantine property. So here it is again. Here's this Diophantine conjecture. It may smell to you like another Diophantine conjecture. So let's move on to step 3. Step 3. Notice the similarity. And if there's time, there might not be time. If there's time, I can explain the proof of this main graph theorem. It's actually a very simple construction based on marked edges and removing an edge and putting it back in. It's a very classical construction. It's kind of shocking that people didn't make this observation before. But even if they had, they maybe wouldn't have had the technology that's been developed for step 3. Similarity to Zaremba's conjecture. Zaremba's conjecture is the following. So this is conjecture to Zaremba from 1972 says there exists an absolute constant A, so that for all Q, or maybe sufficiently large Q, there exists a coprime P with P over Q having continued fraction starting with a 0, A1, A2, up to AK, doesn't matter what the length is, with all partial quotients bounded by A. Okay, so the difference is now we're asking not only for all the partial quotients to be bounded, but also for every other partial quotient to be a 1. So there was some progress on this problem. So there's a number of advancements prior to work of Bergan and myself. But what John and I were able to show is that there does exist an A, so that the number of Q up to X having this property is asymptotic to X. So it's asymptotic to X as X goes to infinity. So a density 1 set of Q does satisfy this property. Less than 1, less than infinity, of course. A can't be less than 1. We need some partial quotients. An important role is played here. Important role is played by delta, which is the Hausdorff dimension of the Cantor set, CA, where CA is the Cantor set, Cantor-like set of, so it's maybe easier to write it. It's just the set of all numbers that are uniformly badly approximable. So these are infinite continued fractions. These are the limit points of the set of fractions that we're interested in, so that all AJ are bounded by capital A. So for example, just to give you an illustration, if A is equal to 2, what does this look like? So we're in the unit interval. The first partial quotient being 1 means that the original number was between 1 and a half. And then if the first partial quotient is equal to 2, then the number is between a half and a third. But once you get below a third, the first partial quotient is already larger than 2. So all of these numbers need to be cut out. Then you go to the second partial quotient, and somewhere over here is a region where A2 is equal to 1, and then another region where A2 is equal to 2, and then this entire range needs to be cut out. And similarly for this partial quotient. And so on. And you continue in this way, cutting out more and more intervals. And what's left at the end, the set of points that remain after everything is removed, that's the Cantor set C2. Okay, does that make sense? And what we really proved, so what Bergan and I proved is that if the Hausdorff dimension of delta A, so these Hausdorff dimensions get arbitrarily close to 1 as you make A larger and larger and larger. The set of not uniformly but just badly approximable. So the union over all CAs is a set of badly approximable numbers, because these are numbers that are bounded by an unspecified quantity. And it's known that delta A goes to 1 as A goes to infinity. In fact, we have rates. Let me not write down the rate. But what we show is that if this Hausdorff dimension exceeds some number sufficiently close to 1, which in our case was 0.98, then we have the conclusion. Then the number of Q less than X, for which the Diophantine property holds, is asymptotic to X. Okay, This work was improved upon. So this work used something I call the orbital circle method. So it's the circle method applied to these thin orbits. I don't have time to say where the thin orbits come from, but I've spoken about this on lots of other occasions. But there's sort of two parts, and one part is a major arcs analysis, and another part is a minor arcs analysis. And for Lenkov and Kahn, soon after our work, so this was, well, 2011, although it only appeared many years later, for Lenkov and Kahn, we're able to reduce this delta, restriction on delta, down to a much smaller number, something like 0.83, at the cost of proving this, weakening this statement to just being positive proportion. And again, positive proportion is plenty for our original application. And then my student, Xinyi Huang, figured out how to combine their improved minor arcs analysis with our major arcs analysis, and to get, for the same value of delta, that this now is back to being a full asymptotic. And then Kahn continued working in this direction. So Kahn let's see, I wrote these down also. Kahn in 2015, got this down to 0.8. So what the necessary value of delta is, down to 0.8, but again, only for a positive proportion. And then in 2017, he kept working on this very hard, 0.781. And then in 2021, he got it down to 0.775. Now, I'll explain in a second why I'm writing these numbers, these numbers so precisely. You know, this is where people start to complain about analytic number theory, that people are just cranking constants for no good reason. And why is this happening? I'll tell you in a second. So our work would apply to the situation of the graph theory theorem, where every other partial quotient is equal to 1, as long as the Hausdorff dimension. So step three is basically done. We've reduced the Diophantine analysis through this Zaremba work. We were able to reduce the Diophantine analysis to a question of dynamics. The dynamical question is, what is the Hausdorff dimension? These methods apply to the setting of, where every other partial quotient has to be 1. And the only question is, does the remaining question, this is part 4, remaining question is, does the corresponding Hausdorff dimension, so let's call this theta A, is the Hausdorff dimension of now the Cantor set, where you start with a 0, you have A1, then a 1, then an A3, then a 1, then A5, then a 1, and this continues forever. And the AJs are all again bounded by A. So the remaining question, does the corresponding Hausdorff dimension exceed these numbers? Known values, now proved values. So it turns out that there was a paper completely unrelated to anything we were doing by Hankel and Turek in 2023. And what they show, so if we let theta infinity be the, in fact, let theta infinity, let me call this theta bar. Let theta bar be the set where you just have any, no restriction at all. Okay, so there's no restriction at all. AJ are arbitrary, except for the fact that every other partial quotient is 1. What they showed is that the Hausdorff dimension, theta bar is already the Hausdorff dimension. So what they showed is that theta bar lies between two numbers, and the two numbers are 0.819 and 0.732. And now let's look back at the known values, and it's completely inconclusive. So what we had to do, the last step, and was to develop. So there's a lot of technology. The problem of estimating, the problem of rigorous estimates, and we're fighting in the second or third decimal place to figure out whether we have a theorem or not. The problem of estimates of these Hausdorff dimensions is also very old. Let me, in the interest of time, not review the entire history, Hausdorff dimension of these fractals, of these kinds of fractals, dates back to the 1920s. There's Good's work in the 1950s. Again, there's a very long sequence of progress, and using techniques of Polycott and Vitnova, we were able to estimate this much more precisely. And the estimate is that it lies between 0.799, that's an upper bound. So we're really in trouble because we're right in the range of where these results run out, and 0.798. So in fact, there does exist a value, and in fact, if A is equal to 110 is some crude value, then theta A exceeds this 0.775. We're allowed to decrease the Cantor sets a little bit and still stay above the threshold, 0.775. And so this is what I mean by we can prove now a positive proportion. And if we wanted to, we could combine that with Huang's analysis and get density 1. It's not necessary for this theorem, so we didn't bother writing it up, but all the technologies is there. Okay, I think that's all the time I'm supposed to take, so let me stop there and take any questions.